Hey everyone, today we're going to talk about function composition. Now function composition is a topic that concerns itself with combining functions. And more accurately, it asks the question, if we have multiple functions acting in sequence, in order, can we write one function whose action mimics that combination of actions by itself? And to illustrate that concept, I've drawn out very explicitly two functions right here. We have f, that inputs from the green set and outputs into the blue set, and g, which inputs from the purple set containing the blue set and goes to the black set. So purple to black. Now I've done this partly because it illuminates a very useful concept about functions, which is that they are like flight plans. What do I mean by that? Well, suppose you want to find f of a, right? Treating f as a flight plan, we think of it as a series of flights connecting the green airports to the blue airports. So, if you're starting at airport A, you have a flight outbound, and if you follow the f flight plan, you could only go to x, right? This is the flight that comes out of A, and you end up at x. Now, the first concept in function composition is what happens if you take the g flight after that, right? What is, in mathematical terms, g of f of a? Well, we just saw that f of a equals x, right? The a flight led us to x. That means that g of f of a equals g of x by substituting directly in. We then can follow the flight out of x under the g flight plan, and we land at n. So g of x is equal to n, and that means if you start at A and you follow the flight plan of f, right? You take f of A, you then end up at some intermediate step, some layover stop, and after that you have to take another flight to get your final destination. Now, we all hate layovers, right? They suck. So the second question is, can we draw up a flight plan that skips the middle step, right? If we only care about this destination here, why not write a new function that mimics this double action just by one action? And that's exactly what we're going to do with function composition. The formal way to write this combined action is g with this little circle called the composition symbol, f, and it's going to input from green, like f does, and output into black, like g does, skipping all these intermediate blue and purple spots. So to figure out what this function is, we'll follow each one. We already know that a goes to n, so we'll draw that in. We see that b goes to w, which goes to l. So we draw b to l. And c goes to y, which then goes to p. So we have c to p. And that is the combined action of f and g. Notice that even though g maps to all five elements or airports in the black set, right? It reaches O, and it reaches M. The combination of G and F cannot reach either of those because the F flight plan never reaches any of the departure points that reach M and O. So M and O become unreachable. So that's a little bit of a quirk of function composition, is that sometimes you lose potential destinations. Okay, so that's all well and good. But as you know, with functions, we usually want to work a little bit more abstractly, right? We don't usually want to be working with functions that we have to draw out completely explicitly. So for my next example, I'm going to go over an example with two functions defined by rules. So we've got f that goes from numbers to numbers, g from numbers to numbers as well. And f of x is going to be defined by x squared minus 1 right here, and g of x will be 2x plus 3. So first let's start with the smaller concept, right? we'll find a particular value as it gets fed through both of them. So we have f of 2 gets sent to 2 squared minus 1, which is equal to 4 minus 1, or 3. And then we've got g of f of 2, which, as we just saw, is equal to g of 3. And that gets sent to 2 times 3 plus 3, or 6 plus 3, or 9. Now, as for the composite function, we know it's got an input from numbers, an output into numbers, so we can draw that in. G composition f, inputs from the numbers back into the numbers, and G composition f of x is where things get a little bit more tricky. Instead of working with a particular value, as we did with g of f of 2, we're going to work with the entire expression for f of x. So g composition f of x is equal to g of f of x, which equals, substituting in, g of x squared minus 1, which, if you plug this into the expression for 2x plus 3, you will get 2 times x squared minus 1 plus 3, which equals 2x squared minus 2 times 1, or 2, plus 3, which equals 2x squared plus 1. Now notice the similarity of our action here, right? When we evaluated g of 3, we plugged 3 in to this sort of framework that we have into this template that the rule for g of x defines. Here, instead of one number, we're going to plug an expression, but the action is the same. All right, let's move on to our final example, a word problem. A shepherd wants to build a square pen for his sheep, one of the many shepherds in math. He wants to give each sheep 4 square meters of space. Each meter of fencing will cost him $4, and the pen gate will cost a flat $20. We want to write a function that relates the number of sheep in the pen to the cost of the pen boundary. Now, the first thing to notice here that this is actually a combination of 3 different relationships. Each one is more direct than the complicated relationship we're going after at the end. We first have the relationship between sheep and area, right? Each sheep needs 4 square meters of space. We then have the relationship between area and length, which is just a geometric property of squares. And finally, we have the relationship between length and cost, where each meter of fencing requires $4 plus a flat 20. Now, each of these intermediate relationships is much easier to write out than the composite relationship directly, right? So we're going to write each of these out by themselves. We start with a function that inputs sheep numbers, or positive integers, to be precise, and outputs pen areas, or positive numbers, to be precise. And we know that this function maps the input, s, to 4 times it, right? We need 4 square meters of space for each sheep, so we have a of s equals to 4 times s. All right. We then look at L, which maps the square area and outputs the square length, hence the name L. We know it takes in area. It's going to output the perimeter of the square. So we're going to need 4 times one side length of the square, which will be the square root of the area. Okay? And finally, we want to take our length and figure out what cost each length will give us, right? We'll have C, this function, that inputs a length of fencing and outputs a total cost in dollars. We'll have C of L maps to, well, let's see, 4 times the length, because each meter costs $4, so 4L, and then plus the flat 20. It remains then to combine all three of these into one monster function that models the combination of these relationships, C composite, L composite A. We know, first of all, that C composite, L composite A is going to input sheep numbers, right, and then output total cost in dollars. So I've written that here. We also know, because we want the composite function to do the same thing as the combined action, that C composite L composite A of x is equal, or should be equal to, C of L of A of S. So a lot of parentheses here. We're going to go from the inside out, like usual. We'll substitute in A of S, so we get C of L of 4 times S, which is equal to C of 4 times the square root of 4 times S, which finally equals to 4 times 4 times square root of 4 times S plus 20. And that will be the final expression that defines our mapping. Now, the benefit of finding the composite function is that you only have to do it once, right? If you had to calculate 3 different costs separately, each individually, you'd have to do this whole nesting expression 3 times. If you simply find the composite function, the composite expression, once you have the expression, you can simply plug in whatever sheep number you need, and then you get the final output without having to go through the intermediate steps a bunch of times. This kind of harkens back to the very start, where we designed a flight plan that avoided all the layovers, right? Well, this avoids the 2 layovers in the middle for all future computations that we might need to do. One final note before I close off the video is that in this video I've deliberately chosen examples where we don't have to worry about domain. However, when the examples aren't so nice, most notably for this class you'll be looking at square roots of numbers and division by 0. When the domain isn't nice, or it has holes essentially, tricky things can happen with domain. In fact, very tricky things. So I'll talk about all those in my video about domain, but for now, just be wary that those situations can come up if you're working on problems like this. But otherwise, that's it for today. This has been Function Composition. Thank you all for watching.